Just so Joseph, for the test, you'll be providing like a formula sheet, effectively, right?
Yes.
Nothing else. Okay, just clearing it up. All right, sorry, continue.
Yeah, let's see if I maybe I can show you an example of a prior test here. So Zoom's fighting with me. Okay.
I'm always gonna print it out and just distribute it. More or less, but.
So, for example, this is a test I gave several years ago for graduate course on microwave stuff. So here I gave gave the students a certain number of formulas, and then they've got a number of questions to work through. It's up to you to figure out which formula to use and how to use them. Okay, so okay, so we're back to looking at the test now. So sketch and label a state transition diagram for a memory-based modulation scheme with, let's say, a constraint length equals L or equal to 2 or 3 or 4. It's not going to be 7, because that's going to get too messy. Do the same but with a trellis, right? So let's go back and look at that. Let's see which one was that. That was probably lecture 5, maybe. So here, this is our state transition diagram for NRZ I. So we can go back and look at what does that mean. We haven't gone into a lot of detail on the different types of signals that we're using on these. So but just understand that, yeah, this one is looking at a prior symbol and updating it. So we have an AK coming in, and it's has this modulo 2 addition with the previous BK minus 1 to output a new BK, right? So that has a memory depth of 1. We're looking at the prior one there, and outputting that result, right? So now we have a the idea we can model this with Markov chains. We just kind of talked about these in a bit of an abstract way, but we know that we can model these. Now we have different states that we can exist in, and we can be in state S0 or state S1, and we transition between these states. If we get a 1N in this case, then we would move to state 1. If we're in state 1 and we get a 1, then we'll move to state 0, right? And these states are, if you get a 0, then you're basically going to stay at that same state, right? So that maps out this function right here. The same type of information can be encoded in a trellis, and here now the trellis gives you a state that is organized vertically. So if you would have 3 states or 4 states, you would end up with moving farther vertically. You would have more states represented vertically, and then horizontally we're evolving over time, right? So here we're moving from time instance 0 to time instance 1, 2, 3, 4, and the state transitions are the same. All of these dots up here represent state 0, but at different times of this overall process, right? As we move from left to right. And but each transition is shown here, where if we're in state 0 and we receive a 0, we're going to stay in state sub-0, right? If we're in state 1 and we receive a 0, we're staying there. But if we receive a 1 from any of those, we transition, right? So same type of information, except this doesn't really well account for the time aspect. It shows you one transition event, whereas this trellis can show how things evolve over time. And you might end up being interested in seeing how that the symbols evolve over time. Okay. All right, let's go back to the test preview. Okay, so all right, draw a PAM PSK or M-Airy Comm constellation. Okay, I'm not sure if I pointed out this notation here. We tend to talk about we could call this a 1024 Airy type Comm or a 8 Airy Comm. This you substitute in the M here, and that's your and tag it with Airy and Comm, and that is going to indicate the size of your constellation. Size of your constellation basically maps to M, capital M, and then we already discussed how you can figure out K from that, right? So constellations can range anywhere from like PAM are just pulse amplitude modulated signal, and that might just encode a few symbols. But if we want to now look at that over a let's see, let me go ahead and oops. Come on. Okay, so PAM is along the real axis only here, and so we can describe that. But when we we looked at PSK constellations, we see now we're actually moving around the complex plane, but still kind of one dimension, because we only have a one circle here, right? But we can now start looking at multiple amplitude levels and multiple phases, and start spreading these constellation points out on the complex plane, right? So remember, now we have what we actually send are pulses, which have a certain shape to them. We haven't talked about what the ideal shapes are yet, but they are shaped over time. So they are a function of time. And so that pulse, though, is then modified. Its amplitude, frequency, or phase is modified based upon your modulation scheme to encode that information, right? And but we can take those symbols that we're sending that are this function of time, and we can represent those with a basis function expansion, like you might do a Fourier series expansion in a similar way. And then we can just draw these constellations using that vector representation. That vector representation is kind of abstracts away the time dependency and encodes that whole complex symbol over that is a function of time as a single vector. And then we represent that vector as a point in the complex plane. We just, again, for the sake of time, in an undergraduate course, we kind of skipped over a lot of that derivation of those basis functions and stuff. So I'm not going to, hold you accountable for that type of thing, but just, so you understand that these constellation points here are the vector representations of that signal, right? And then we have the quadrature AM here. So now here we would talk about this being a 8 across by 8 down. That's 64 points. So that'd be a 64 area Comm type signal, right? So all right. Write a gray code for this constellation. You did that as a homework assignment. It's not terribly hard to do for a small constellation. You can just kind of brute force it, try a few things, and really look at a understanding the concept that a gray code, you're only flipping one bit at a time for the adjacent constellation points, the ones closest to it. Obviously, it gets a lot more challenging for larger constellations. There is there's a few things online here. I will include a link to this site over here where it kind of gives you a methodical approach that I think is easy to kind of understand about how to generate those. If I do ask you about a gray code, it's going to be pretty simple, small constellation. So but yeah, you should understand that the gray code, as you move between points that are closest together, that only one input bit changes, right? So this would be a 4 symbol, m is equal to 4 type constellation, and this would be an m equals 8 type constellation. And so as you move from one symbol to another, again, you might have some error in estimating that proper symbol, but if it's you're most likely to choose the adjacent symbol, right? One of the nearest constellation points. That's where you're going to make that error most likely, right? Unless your noise is just horrible. And therefore, you're only going to be off by 1 bit. And it's a heck of a lot easier to fix 1 bit than it is 2 or 3, right? So, all right. Okay, FSK modulation, what is the closest spacing to still have orthogonal signaling? We did a little derivation there, and we ended up drawing like a sync x over x type plot, sin x over x or sync x type function, and noted that we have a minimum spacing if we squeeze these things together too closely for too high data rate, then we're not going to be able to separate out the signals. They're all going to look like they're blending together in terms of frequency. So if we're and that's a function of the symbol rate. So you'll that relationship is tying together the symbol rate and the frequency deviation that's involved in this frequency shift keying. So I will provide that equation, but yeah, you just need to know how to plug and chug on that formula. Understand the basis of a map receiver and how Bayes' theorem factors into it. These are from our latest lessons, not asking you to derive the map receiver, but understanding that we're maximizing the posteriori probability, and we use Bayes' theorem to flip around the conditionals. And then important to understand that if all of our bits are equal probable, then we can determine that the probability actually of M, the message being sent, so it's not just the bits, but it's a little bit more the probability of the symbols being sent, that if they're all equal probable, then the mean is just 1 over M, and we can ignore that. And now we're left with a maximum likelihood, or an ML type receiver, a little bit simpler. Work with decision areas. So I might give you some sort of constellation and ask you to sketch the boundaries of the decision areas, right? And so that is fairly straightforward if the symbols are equal probable. If they're not equal probable, then it gets a little bit more complex, and I would again give you that equation that would have the bias term, and you would just need to understand that bias term that's influenced by the probability of which message being sent, how that affects the decision area, right? So if a particular message is much more probable, then you tend to use a larger decision area to account for that higher probability to get the best net error rate out of it, right? So and then finally calculate the probability of error using a Gaussian distribution and Q function, and we did that as one of our last lectures, I think, but it turns out you also did a little bit of a homework assignment on that. So let's sorry, we're kind of running out of time. Where is the homework? There it is. So all right, so I'll go over the homework real quick, and we're probably going to run out of time here, but since I know we had a few people walk in late, we're going to keep the test scheduled for next Tuesday, and apologize for that conflicting with the career fair. I would normally do that, but I just didn't know about it, and we decided not to change that date. So we still have Friday's lecture to cover any questions. It would be helpful if you do have questions to either attend my office hours, make an appointment with me, or if it's something that makes sense for me to address during the lecture on Friday, then yeah, send me an email in advance if possible, and I can make sure that I'm prepared to answer that question in the best way I can.
Professor?
Yeah.
There's one question. Will this be posted on Moodle, the homework and the answers?
Yeah.
Cool.
Yeah.
Thank you.
Yeah, let's see. All right, random experiment consisting of drawing a ball from an urn that contains 4 red balls numbered 1, 2, 3, 4, and 3 black balls numbered 1, 2, 3. Okay, this is one of these classic toy problems that we see in probability and statistics, and we set up one event where the number of the ball is even. So we don't care about the color. We just care that the ball is even, right? And then event 2, this is both the color of the ball is red and the number is greater than 1, right? So that's an intersection we're talking about there, right? So and so on. So now what is the probability of event 2? Well, let's look at all the events. There's 7 different events, right? Because there's 7 different balls. We're doing one draw, and so what is the probability of E2? That the color of the ball is red and its number is greater than 1. Well, just count them up, right? So if it's red, we're looking at the event 2 is R2, R3, or R4, right? So there's 3 different events that could occur that would satisfy E2. But a total of 7, right? So that's 3 sevens. Now we look at the conditional. What is the probability of E3, given that we know that E2 was satisfied? So you can write this out as that intersection divided by the marginal probability there of E2. Up here, this is a probability that we're going to have an R2, right? So if you look at this, the number of the ball is less than 3, but it still needs to be red and greater than 1. Well, there's only one event that satisfies that, and that's R equals it's a red 2 ball, right? So probability of drawing a red 2 ball, there's only one of those, so that's 1/7, and but the probability of E2 is 3/7, so it's really 1/7 divided by 3/7, and 7s cancel out, so you have 1/3 there, right? So times it. So so you just keep doing that same type of process. This notation was a little bit confusing in the book. It's basically the book that I drew this example from, and but you're basically saying that both E4 and E3 have occurred, and so just write these things out. E4 is a union of E1 and E3, so you can kind of write the number of the ball is even. So that's the 2s basically, and regardless of color, and then E3 is the number on the ball is less than 3. Well, that also includes the ones, right? So you write those out. So there's 1, 2, 3, 4, 5 different possibilities, balls satisfying E4. Do the same with E3. Look at the intersection of these, which ones show up in both, and write that out. And now you can look at how do we calculate this conditional. Well, we put the intersection of all the events, probability of all the events up top occurring, and the probability of that's E3 and E4, right? So probability of that conditional happening, right? So and that should then give us that probability of E2, right? Given that E4 and E3 have occurred. So again, just total up the balls, and you end up with this top one being represented here. There's just one ball there, 1/7, but the probability of E4, E3 is 4 balls out of 7. So again, that's 1/4. All right, then are E3 and E5 independent? So let's go ahead and you go through and calculate these things, and you say that, well, is the probability of E3 and E5 occurring equal to or not equal to the probability of E3 times the probability of E5? Are they independent, or is there do we need to handle them with this conditional type of toolbox that we have? So you can just go through this, calculate it the same way. You have 2 7s, well, on one side, and 4 7s times 3 7s on the other side, and so those not equal, and so they're not independent. They have some influence between each other, right? Okay, I know I'm going faster here, but you can you'll be able to look at these and I understand them, hopefully. So all right, and here, this is much like our probability of error. It's the same basic type of approach to the calculation, and but here we've just kind of simplified it, right? We're not dealing with all the symbols and bits and that type of thing. It's just noise in electric circuit that can be modeled as a Gaussian random variable with mean equal 0. That's handy, and variance equal to 10 to the -8. So that's sigma squared, right? Sigma squared is equal to 10 to the -8. That means sigma is the square root of that, or 10 to the -4. Right? And so now, what is the probability that the value of the noise exceeds 10 to the -4? So let me what's my stop share, change camera. So we're going to have some probability density function, a Gaussian, and it's 0 mean, okay, but it's sigma is going to, sigma squared is describing the width here, right? And so what we're interested in is what is the probability that the value of the noise exceeds 10 to the -4th there, right? So so we would be looking at this area. It's so we're looking at that part of the tail of the Gaussian distribution. What is the probability that it's between -2 times 10 to the minus fourth and 10 to the minus fourth, right? So now we're looking at that region, right? So so we'll use the Q function to do all of that. And all right. Hopefully Zoom is caught up with you. It's slow on my end, sorry. So think through how you want to set up the problem based upon this and understanding what the Q function is giving us here, right? So if the probability, if we're starting with a Gaussian random variable, first of all, then the Q function applies, right? And so what is the probability that X is greater than, well, some alpha? Then that's equal to Q alpha minus the mean. In our case, the mean is 0, divided by sigma, right? Not the variance sigma squared, but sigma, right? And so plug and chug here. Alpha, we're interested in 10 to the minus fourth. It's 10 to the minus fourth, and our sigma is 10 to the minus fourth. So that's just Q of 1. You go to the table and you look it up, and it's 0.154. Okay. So then what is the probability that X is greater than 4 times 10 to the minus fourth? Well, you just, still mean is 0. So now you just substitute in 4 times 10 to the minus fourth, and now you end up with, Q of 4. You look that up in a table. Okay. And now this is the one where you're looking at a range.
The n in the Q function.
I'm sorry?
What does the m represent?
The mean.
Okay.
In this problem, the mean is 0, with a mean equal to 0, so it's simplified. Right. But normally, yes, you would need to carry along that m value, right? So this last one requires you to use some of the principles of the Q values here. And so you can look back at that lecture I did a few times ago, I think was at lecture I guess that was lecture 7. Yeah, lecture 7. Let me switch to that here real quick. And we see these kind of properties of the Q function. The f of x is equal to 1 minus this. So boy, it's slow right now. I'm sorry. So these relationships here should help you, right? So this applies when it's a normal distribution where we're defining the m and the variance, right? And so the probability that x is greater than a certain alpha is this. The probability that x is less than a certain alpha is you swap the numerator, then you can use this equation. So Q of minus x is equal to 1 minus Q of x, right? So if this is x, then this is minus x, right? We just multiplied by -1 there to flip the numerator around. So this is the relationship you're using there, right? So okay, so now you just kind of plug and chug there by referring back to some of your prior answers there, right? And then what is this last one? Given that the noise is positive, what is the probability that it exceeds 10 to the minus fourth? So here it's a conditional, right? So we know that it's greater than 0. So we're not asking for the probability that it's greater than 10 to the minus fourth in all cases. We're only asking for the situation where we already know that the noise is positive. Now, what is the remaining probability, right? I'm using that term loosely, but this is setting up a conditional probability, given that the noise, that the value of the noise is positive. So that's that part of the conditional on the right-hand side of that vertical bar when we write that out. And then what is the probability that it exceeds 10 to the minus fourth? So we come down here. This is that first part. Given that the noise is positive, what's the probability that it's greater than 10 to the minus fourth? This is a conditional, right? So now we put that in. X is both 10 to the minus fourth, greater than 10 to the minus fourth, and greater than 0. But of course, that simplifies then to X is greater than 10 to the minus fourth. We calculated that before, and that's 0.159. What is the probability? Now we put that conditional, the probability of that part of the given part of it. We put that in the denominator. What is the probability X is greater than 0? That's 0.5. You can grab that from the table, but that's also a well-known value that's on that slide I just showed you. All right. Just got a minute left. So this one here, you're basically setting up, understanding that these are a bunch of conditionals. And so you're going to set all those up, but using Bayes' theorem or formula to go from this direction of the conditional to the other direction. Again, I'm using those terms loosely, but hopefully that helps. When we first wrote this down, it was basically for 2 events. Here we have multiple events going on. So we have the idea that we could have 3 different interferers. But if one of those interferers happens, then so these are the probabilities of those interferers happening. So they're not equiprobable. The probability that the system will fail given A1 is this, right? So that's really your situation, right? The probability of failure is conditioned upon which symbol was sent, right? Or which interferer is experienced, right? So here it's just kind of interesting that the most there's look at the effect of the probability of interference with the significance of the interference, right? And so then finally, real quickly, so you can look at these, I'll upload these now after class, show that the random process where theta is uniformly distributed random variable in the range of 0 to 2 pi is Whiteson stationary. So we're going to calculate the mean and observe that it's a constant, right? And so this is just calculating the mean. And then we're going to, but that's a function of the random variable, right? So that's one of the questions I said might be on a test. It's calculating the mean of a function of a random variable. And then we can look at the autocorrelation, auto covariance of this thing. And so here it's handy to use your trig identities. I think I gave you that hint in the previous lecture with these double angle angle formulas, adding and subtracting. You take advantage of these, and you can write this out. The integral limits are updated